Section 3.7, Rational Functions. In this section, we're going to focus on the properties of rational functions and how to graph rational functions. Rational functions are any function that can be written in the form of f of x equals p of x over q of x, where p of x and q of x are polynomials, but q of x is non-zero. One thing to note about rational functions is that all polynomials are actually rational functions. If p of x is a polynomial, then any polynomial p of x can be written as p of x over 1. However, the reverse is not true, as we've seen in the previous sections. Not all rational functions are necessarily polynomials. Even though we're defining a new family of functions, the idea of finding the domain and the intercepts of rational functions is exactly the same. For example, if we want to find the domain of our rational function, we know the one number we're not allowed to divide by is 0. So in order for f of x to be defined, that means our denominator, x squared minus 3x minus 4, cannot be 0. We can solve this equation by factoring. X squared minus 3x minus 4 factors into x minus 4 times x plus 1. If x minus 4 cannot be 0, that means x cannot be 4. And if x plus 1 cannot be 0, that means x cannot be negative 1. So our domain would be all real numbers except for negative 1 and 4, which would be the interval negative infinity to negative 1, union negative 1 to 4, union 4 to infinity. Next, we're going to find the intercepts. Recall from college algebra, there are two types of intercepts, an x-intercept and a y-intercept. To find the y-intercept, which is where the graph crosses the y-axis, we set x equal to 0 and plug it into our function. And we get f of 0 equals 0 squared minus 4, all over 0 squared minus 3 times 0 minus 4. And if we continue to follow order of operations, we get that f of 0 equals 1. So our y-intercept is the point 0, 1. Next, we'll find the x-intercept. The x-intercept is where our graph crosses the x-axis. So here we're going to set our function equal to 0 and solve for x. Now we can solve this equation by using the clearing denominator strategy. We'll multiply both sides of our equation by the x squared minus 3x minus 4. Anything times 0 is 0. So now we need to solve x squared minus 4. We'll add 4 to both sides, then take the square root, and we get x equals plus or minus 2. One thing to be careful of when solving rational equations like this is we need to make sure our solutions are in the domain of our function. If we take a look at 2 and negative 2, notice that those values of x are within our domain, meaning if I plug in 2 or negative 2 in my function, it will be defined and it will give me 0. So both 2 and negative 2 do correspond to x-intercepts, and our two x-intercepts here are 2, 0 and negative 2, 0. Next, we're going to take a look at g of x, which equals x squared plus 3x plus 2 all over x cubed plus 4x squared plus 4x. Starting off with the domain, just like our previous example, since rational functions involve division and the one number we can't divide by is 0, then our denominator cannot be 0. Just like with the previous example, we're going to try to factor our denominator. We see x as a common factor, and the x squared plus 4x plus 4 can be factored farther, and the x squared plus 4x plus 4 factors to x plus 2 squared. And by setting each factor equal to 0, we get that x cannot be 0 or negative 2. And our domain would be all real numbers except for 0 and negative 2, which can be written as negative infinity to negative 2, union negative 2 to 0, union 0 to infinity. Next, we're going to find the y-intercept, which means we set x equal to 0. However, if we take a look at the domain that we found earlier, we already know that 0 cannot be in the domain, which means we cannot plug 0 into our function g of x. Well, if we can't plug 0 into g of x, can there be a y-intercept? No. So our function g of x does not have a y-intercept. If you did try to plug x equals 0 into g of x, you'll still see that there is no x-intercept because your denominator would become 0. And remember, anytime we try to divide by 0, that will be undefined. Next, we'll find the x-intercept, which means we set our function equal to 0 and solve for x. Now, you saw before that in order to solve this equation, we would clear the denominators. And if you watch the previous example very closely, that resulted in the numerator being equal to 0. Anytime you have a rational function written in the form of a polynomial divided by a polynomial, the only way that rational function can be 0 is if the numerator is 0. So to solve the equation x squared plus 3x plus 2, we'll factor just like usual. So we get x plus 2 times x plus 1 equals 0, which means x equals negative 2 and negative 1. But once again, we have to be very careful and pay very close attention to our domain that we found in the first part. Negative 2 is not in the domain. If we try to plug negative 2 into our function g of x, we will not actually get 0. We would get something that's undefined. So for that very reason, negative 2 would not be a valid solution to this equation, and negative 2 could not correspond to an x-intercept. Since negative 1 is in the domain, the negative 1 is indeed the location of our x-intercept. So here we only have one x-intercept, which is the point negative 1, 0. One thing to keep in mind with this example is it is possible for rational functions to not have y-intercepts. It's also possible for rational functions, just like polynomials, to not have x-intercepts. Make sure you're very careful whenever you're solving your equations, especially for the x-intercept, and check to make sure your solutions do not make your denominator 0. In other words, you make sure that your solutions are actually in the domain of our function. Any solutions that are not in the domain or make our denominator 0 when plugged in have to be thrown out. Next, we're going to find the domain and intercepts of h of x, which equals x cubed over x squared plus 1. Since this is a rational function, to find the domain, just like what we did in the previous examples, we want to check to see when our denominator will be 0. If we solve the equation, we get that x cannot be plus or minus I. Whenever we're analyzing the domain or range of a function, we're only concerned with the real values of our variables. Since the only way x squared plus 1 can be 0 is if x is an imaginary value, that means no matter what real number I plug in for x, my denominator cannot be 0. So through solving, there is no real number to remove from the domain, which means our domain is the set of all real numbers. For the y-intercept, we set x equal to 0. Since 0 is in our domain, since there is nothing removed from the domain, it is worth our time to plug in 0. And when we plug 0 into our function h and simplify, we get 0. So our y-intercept is the point 0, 0. Last but not least, we'll find our x-intercept, which means we're setting our function equal to 0. Well, the only way our fraction can equal 0 is if our numerator is 0, so x cubed equals 0, and if we cube root both sides, we get that x equals 0. So our x-intercept is also the point 0, 0. So it is possible for rational functions that are not polynomials to have a domain of all real numbers. Keep in mind, we're only concerned with real solutions here. When we introduced polynomials near the beginning of this unit, we introduced arrow notation to help us describe the end behavior of the polynomial functions. Whenever x approached negative infinity, that represented x decreasing without bounds. Whenever x approached infinity, that represents x increasing without bounds. And with our discussion of polynomials, either f of x approached negative infinity, meaning f of x decreased without bounds, or f of x approached infinity, which represented f of x increasing without bounds. When it comes to rational functions, since there are real numbers omitted from the domain of rational numbers, we do want to try to analyze the behavior around the values that are excluded from the domain. To help us be able to discuss that, we do have to introduce more to the arrow notation. Suppose we say x approaches a with a plus sign superscript. This notation represents x approaching a from the right. To understand what this means, suppose we have a number line, and here is a. To approach a from the right, that means we're starting somewhere to the right of a, and we're getting closer and closer to a. Another way we can approach a is we could approach a from the left. To represent that with the arrow notation, we're going to write x approaches a, and we're going to use a superscript of a minus sign. What approaching a from the left means is we're going to start at some location to the left of a, and we're just going to move our way closer and closer to a. Keep in mind that the plus and the minus are not exponents. These are just to represent which side of a x is approaching from. Now, with polynomial functions, their end behavior either increase or decrease without bounds. But we're going to see later on that rational functions, their end behavior can approach a value. So for that reason, the statement f of x approaches b can also be written in arrow notation, f of x with the arrow, then b. To help you understand the arrow notation, there's a table for you provided in the handout. Please take some time to review that table. Now we're going to use the graph to answer the following. First, as x approaches negative infinity, f of x approaches blank. Here we're trying to look at what our function is doing on the far left, since x is decreasing without bounds. If we look at our graph very carefully, we can see the left part of our graph is getting closer and closer to the dotted line, which is the line y equals negative 1. So as x approaches negative infinity, we can see f of x will approach negative 1 because it's approaching that dotted line. Now for the next question, as x approaches infinity, f of x approaches blank. Since x is approaching infinity, that means we're looking at what our graph does when we go to the far right. But we can see at the far right, our function, our graph, still approaches the dotted line y equals negative 1. So as x approaches infinity, f of x will still approach negative 1. Now we'll try to answer as x approaches 1 from the left, f of x approaches blank. In order to answer this question, first note that x equals 1 occurs on this dotted line here that I'm highlighting a little bit of in pink. And because of the superscript, that means we're approaching 1 from the left. So if I pick a point to the left of 1 on my graph, but still very close to x equals 1, which let's say we pick there, and we're going to trace until we get closer and closer to the line x equals 1, which is this blue dotted line here, we can see that our graph is increasing without bounds. So as x approaches 1 from the left, f of x approaches infinity. Next, as x approaches 1 from the right, f of x approaches blank. This time, I want to be to the right of 1. I'm going to pick a point close to x equals 1, which let's say we pick that point there. And then I'm going to trace my graph until I get closer and closer to 1. You can see as we do, our graph decreases without bounds, meaning f of x approaches negative infinity. Now we'll take a look as x approaches 3 from the left, f of x approaches blank. The line x equals 3 is the dotted line that I'm putting the orange mark on. Since I'm approaching 3 from the left, I want to start at a point close to x equals 3 on my graph, say here, and then trace my graph until I get closer and closer to the dotted line. And you can see as we do, our graph increases without bounds. So as x approaches 3 from the left, f of x approaches infinity. Next up, as x approaches 3 from the right, f of x approaches blank. So here I want to pick a point on my graph to the right of 3, say here, and then trace as we get closer and closer to x equals 3. And when we do, we can see that our graph decreases without bounds, meaning f of x approaches negative infinity. Next, we'll answer as x approaches negative 2 from the left, f of x approaches blank. I'm going to highlight the line x equals negative 2 with that little pink marker. Since we're approaching negative 2 from the left, I'm going to pick a value to the left of negative 2, and then I'm going to proceed to trace the graph as we get closer and closer to negative 2. And you can see as we trace our graph, f of x will approach negative infinity. As x approaches negative 2 from the right, I'm going to pick a point on the graph to the right of negative 2, and then proceed to trace the graph as we get closer and closer to x equals negative 2. And we see this time our graph increases without bounds, which means f of x will approach infinity. A couple things to note about our answers. First, just because we approach from the left or the right, that does not determine what kind of infinity we're approaching, whether it be positive or negative infinity. You do have to make sure you are checking your graph. Also, it is possible for us to approach a number from one side and the other side and both approach the same infinity. So don't make assumptions that when you approach a value from opposite sides, that you are going to get opposite infinities like we have here. That's not always going to be the case. Now we're going to discuss something called asymptotes. There are several different types of asymptotes, but first we're going to find the vertical asymptote. The line x equals b is called the vertical asymptote of f of x if f of x either approaches positive infinity or negative infinity when x approaches b from the right or the left. If you recall from college algebra, if our function is f of x equals log of x, then f of x approaches negative infinity as x approaches 0 from the right, as we can see from the graph of our logarithmic function down here. So x equals 0 was a vertical asymptote for the function f of x equals log of x. Another way to think of vertical asymptotes, they're the lines where our function, as we get closer and closer to that line, begins to either increase or decrease without bounds. So if we take a look at the graph that we saw in the previous example, notice how as our function gets closer and closer to line x equals -2, whether it's from the left or the right, we see it either approaches infinity or negative infinity, and it only takes one side to approach one of the infinities, then our vertical asymptote is x equals -2. Notice how we're saying x equals -2, not just -2. Vertical asymptotes are vertical lines. Vertical lines are written in the form of x equals a number. But we can also see this characteristic as our function approaches 1 from the left or right, or as our function approaches 3 from the left or right. So x equals 1 and x equals 3 will also be vertical asymptotes of our graph. Let's suppose f of x equals p of x over q of x is a rational function where p of x and q of x have no common factors. Then the real zeros of q of x are going to correspond to the locations of the vertical asymptotes of f of x. What this means is if we have a rational function, we reduce it into simplest terms by canceling out all common factors. All of the zeros of the denominator of the resulting simplified form will tell us the locations of the vertical asymptotes. Now, any value that's excluded from the domain that are not the locations of vertical asymptotes are referred to as removable discontinuities, which we often call holes for short, because we can think of them as locations where the graph is punctured at a single point. Now we're going to find the vertical asymptotes and the location of the removable discontinuities of the following functions. Since we're trying to find the holes and vertical asymptotes of these rational functions, the first thing we want to do is we want to factor the numerator and denominator and try to cancel all common factors. So x squared minus 4 factors to x minus 2 times x plus 2, and x squared minus 3x minus 4 factors to x minus 4 times x plus 1. Notice how there's no factors to cancel out. So if we use the information from the previous slide, our vertical asymptotes are going to be located where our denominator is going to equal 0, which is going to be x equals 4 and -1. So x equals 4 and x equals -1 will both be our vertical asymptotes. Are there any holes? No. Since we didn't cancel out any factors, there will be no holes in the graph of our function. In other words, there will be no removable discontinuities. Now we'll take a look at g of x, which equals x squared plus 3x plus 2, all over x cubed plus 4x squared plus 4x. If you recall from the example 1 that we did when we found the domain, the numerator factors to x plus 2 times x plus 1, and the denominator factors to x times x plus 2 squared. Now when we reduce, an x plus 2 will cancel, which leaves us with x plus 1 over x times x plus 2. Now we'll set our new denominator equal to 0, and we get x equals 0 and -2. And our vertical asymptotes would be x equals 0 and x equals -2. Now, we do want to be careful, make sure we are tracking our canceled factors. Any factors that cancel usually correspond to the location of a hole. So if I manipulate this, if x plus 2, our cancel factor equals 0, that means x would equal -2. So it's very tempting to say we would have a hole at x equals -2, but it's impossible for a graph to have both a vertical asymptote and a hole at the same time. So what should our graph have, a vertical asymptote or the hole at x equals -2? If our graph has a vertical asymptote at a location, it is impossible for it to have a hole. So since x equals -2 would be the only possible location for a hole, but we already have a vertical asymptote there, that tells us we have no holes. We'll find the vertical asymptote in the holes of x squared minus 1 all over x cubed minus x. We'll start by factoring. Our numerator becomes x plus 1 times x minus 1. Our denominator is x times x minus 1 times x plus 1. The x plus 1s and the x minus 1s cancel. We get 1 over x as the simplified form of our function. Now to find our vertical asymptotes, we'll set our new denominator equal to 0. Since our denominator is x, then that means x would equal 0. So our vertical asymptote would be located at x equals 0. As for our hole, we can figure out the location of our holes by taking the factors we canceled out, which would be the x plus 1 and the x minus 1, and setting them equal to 0. So here we have two holes, one located at x equals -1, and the other located at x equals 1. Now holes, you can think of as punctures in a graph. If I want to know the exact y-coordinate of the puncture, I can take the x equals -1 and 1 and plug it into our reduced form. If I take -1, plug it into the reduced form of our function, we get -1. Well, if I take +1 and plug it into our reduced form, I get +1. So the holes of my graph are going to be located at x equals -1, which would be the point -1, -1, and the point 1, 1. Basically what's happening here with this graph, so if I draw a little sketch, our graph of h of x is going to look exactly like the graph of 1 over x, except for at the points of 1, 1 and -1, -1, I'm going to have these punctures, these holes. And my graph of h of x looks almost exactly the same as my graph of 1 over x, except for those 2 points at 1, 1 and -1, -1 are removed from the graph of 1 over x. Now, it's very hard with technology to see what holes look like because points are getting arbitrarily close to the holes, so technology may not necessarily be able to highlight that you have a hole located at certain locations. The second type of asymptote we're going to talk about are called horizontal asymptotes. The line y equals a is called a horizontal asymptote if f of x approaches a as x approaches infinity or negative infinity. In general, a function can have at most two horizontal asymptotes. Polynomial functions, which we studied earlier, have no horizontal asymptotes since f of x would approach infinity or negative infinity as x approaches infinity or negative infinity. Rational functions are a bit special. We'll discuss those later when it comes to their horizontal asymptotes, but we will see later on in this course functions that do have two different horizontal asymptotes. Because horizontal asymptotes are defined based off of x approaching infinity or negative infinity, horizontal asymptotes are used to describe the end behavior of the function. If we take a look at the graph below that we've seen in previous examples, if we look at the left end, we can see the left end approaches the line y equals -1. So y equals -1 is a horizontal asymptote of this graph. Notice that I'm saying y equals -1, not just -1. Horizontal asymptotes are horizontal lines, just like vertical asymptotes are vertical lines. So we have to represent them with the appropriate equation, and horizontal lines are always written in the form of y equals a number. As for the right end, we can see the right end also approaches -1, so our graph does only have one horizontal asymptote, which is y equals -1. But keep in mind, it is possible for a graph to have at most two horizontal asymptotes, so you do want to check both ends to make sure you don't have multiple horizontal asymptotes. Another misconception some people have about horizontal asymptotes is that our graph of a function can never cross a horizontal asymptote. That is an incorrect misconception. If you look at our graph here, you can see at that portion of the graph, it does cross our horizontal asymptote. So horizontal asymptotes are not lines that our graph can't cross. They are lines that our left or right end of our graphs get closer and closer to. Now we're going to discuss how to find the horizontal asymptote of a rational function without the graph. Rational functions are special when compared to other functions because they're only going to have at most one horizontal asymptote. If the rational function does have a horizontal asymptote, then both ends of the function will approach the horizontal asymptote. We're going to let f of x equals n of x over d of x be a rational function. And we're picking n of x to represent the numerator, d of x to represent the denominator. The way we can determine whether or not our function has a horizontal asymptote or not and where that horizontal asymptote is located is by comparing the degrees of the numerator and denominator. If the degree of the numerator is greater than the degree of the denominator, then f of x will not have a horizontal asymptote. This is because the numerator is going to grow at a much faster rate than the denominator, causing the entire rational function to increase or decrease without bounds because the numerator is growing so much faster. On the other hand, if the degree of our numerator is less than the degree of the denominator, then our horizontal asymptote is going to be at y equals 0. The reason why this is the case is this time our denominator is the one that's growing much faster. And since our denominator is growing faster than our numerator, that's going to drive the value of our rational function closer and closer to 0. But what happens if our numerator and denominator have the same degree? If our numerator and denominator have the same degree, then our horizontal asymptote will be y equals a of n over b of n, where a of n and b of n are the leading coefficients of our numerator and denominator, respectively. And this is because both of our numerators and denominators are growing at the same rate. So they have this stabilizing effect where they get closer and closer to the ratio of their leading coefficients. Now we'll find the horizontal asymptotes of each of the following functions. Notice all three functions are rational, so all we have to do is compare their degrees to determine if they have a horizontal asymptote and where that horizontal asymptote is located. If we look at the numerator of f of x, we see that's a degree 4 polynomial, while the denominator is a degree 3 polynomial. So here, the numerator has a higher degree than the denominator, which means f of x does not have a horizontal asymptote. If we take a look at g of x, we can see that the highest power in our numerator is 4, so the numerator is a degree 4 polynomial. As for the denominator, we can see that the highest power is actually our middle term, which means our denominator is also degree 4. Because our degrees are equal, that means g of x does have to have a horizontal asymptote. Our horizontal asymptote will be y equals the ratio of our leading coefficients. In our numerator, 5 is our leading coefficient. In our denominator, -4 is the leading coefficient. So our horizontal asymptote is y equals -5 over 4. Last, for h of x, the numerator is degree 5, while the denominator is degree 6. Since our numerator has the smaller degree, that means h of x does have a horizontal asymptote, which will be y equals 0. Now we're going to write the equation of the function graph below. Now these can be a little bit tricky to do, but we can figure this out by using what we've learned about zeros, invertical asymptotes, and holes so far. First, notice that there are no holes to the graph, and we know that vertical asymptotes come from setting the denominator equal to 0. We can see here that there are two vertical asymptotes, x equals -2 and x equals 2. That means 2 and -2 were both zeros of our denominator. And if you recall from our previous section, that means that x plus 2 and x minus 2 would have to be factors of our denominator. Now, how do we figure out the numerator? The numerator, when set equal to 0, would tell us where the zeros or x-intercepts of our graph would be, which we can see on our graph that there are two x-intercepts, which are at 1 and -1, which means when the numerator is set equal to 0, the solutions would be 1 or -1, which means x plus 1 and x minus 1 would have to be factors of the numerator. We know what the factors of the numerator and denominator are, but we don't quite know what the leading coefficient of our numerator and denominator are. But we know in the factored form, we know the leading coefficient, which let's call a for the numerator and b for the denominator, would have to be there. Now, because of the division, we could simplify this a little bit farther. Instead of just focusing on two variables, a and b, treating them as two different unknowns, let's consolidate them into a single unknown value, which we're going to call a. Now, the problem is, one, how do we know we're not missing any factors? If we take a look at the fact that we have a horizontal asymptote, we know that the degree of the numerator cannot be larger than the denominator. So they can either be the same degree or the denominator is the one with the larger degree. But we know if the denominator had a larger degree, our horizontal asymptote would have to be y equals 0. But we can see from the graph our horizontal asymptote is y equals 4. That tells us the numerator and denominator must have the same degree. Our numerator is degree 2, our denominator is degree 2. Everything is checking out so far. But how do we figure out the value of a? The only thing we haven't used yet is the fact that our graph has to pass through the point 0, 1. Since 0, 1 is a point on our graph, that tells us f of 0 must equal 1. So if I plug 0 into my function as we have it now, it should equal 1. So we have a times 0 plus 1 times 0 minus 1 all over 0 plus 2 times 0 minus 2 equals 1. Do a little simplification, and we get 1/4 a equals 1, which means a equals 4. So now that we know that a equals 4, that means f of x equals 4 times x plus 1 times x minus 1 all over x plus 2 times x minus 2, which if we FOIL and expand, keep in mind we're treating the 4 as 4 over 1, we get 4x squared minus 4 all over x squared minus 4. One thing to note in this particular example here, we could figure out a was 4 without doing this extra work in this case, and that's only because the capital A did represent the leading coefficient of the numerator divided by the denominator, which we knew had to be 4 because that's where our horizontal asymptote was located. However, if we didn't have a horizontal asymptote, or if our horizontal asymptote was y equals 0, we would have to go down the route we did to figure out what the value of a would be. So sometimes there is a shortcut, like in this example here, but it may not always appear. Even though some rational functions do not have horizontal asymptotes, we can still describe their end behavior by using something called slant asymptotes. A slant asymptote is a non-horizontal line that the left or right end of a function will approach. Specifically for rational functions, in the form of n of x over d of x, the rational function will have a slant asymptote when the degree of the numerator is exactly 1 greater than the degree of the denominator. Note that a rational function will not have a horizontal asymptote if the degree of the numerator is exactly 1 more than the denominator, but it will have the slant asymptote. If we take a look at the examples below, since g of x is a rational function where the numerator and denominator are both degree 4, then g of x has no slant asymptote. Same thing goes for h of x. Since the numerator has degree 5, while the denominator has degree 6, then h of x cannot have a slant asymptote. If we take a look at f of x, which is degree 4 in the numerator and degree 3 in the denominator, then f of x will have a slant asymptote. But how do we find the slant asymptote? The way we find the slant asymptote is we're going to divide the numerator by the denominator, and our slant asymptote will be the quotient of the division. So since we know f of x does have a slant asymptote, we can find it by performing the polynomial division. Now, unfortunately, since our denominator is degree 3, we cannot use synthetic division, but we can still use long division. So we'll set up our polynomial division, and we'll begin to divide. Remember that when you are setting up the polynomial division, remember to include zeros for any missing terms, such as the x squared term in the denominator, or the x cubed, x squared, and x term in the numerator. Now we'll proceed to divide. 3x to the fourth divided by 5x cubed is 3/5 x. Multiply, and then subtract. Now when we subtract the 3x to the fourth minus 3x to the fourth is 0. 0x cubed minus 0x cubed is also 0x cubed. And since we haven't found a non-zero term yet, we can cancel them out as well. And 0x squared minus negative 6/5 x squared is 6/5 x squared. 0x minus negative 9/5 x will be 9/5 x. And then we can bring down the negative 4. Now since what we have remaining is a degree 2 polynomial, we cannot divide any farther. Keep in mind though, for our slant asymptote, the only thing we're concerned with is the quotient. We don't care about the remainder. So our slant asymptote will be the line y equals, and our quotient from the division, 3/5 x. So as x gets larger and larger or smaller and smaller, the graph of f of x is going to get closer and closer to the line y equals 3/5 x.